This is part 7 of the series Logarithmic, Exponential, and Other Transcendental Functions. In the last video, we talked about the existence of an inverse function, how you can determine if a function has an inverse function, and then we actually looked at it. That leads us up to a discussion of continuity and differentiability of inverse functions. Let's start by considering a function f that has a domain on some interval I. And let's also say that f has an inverse function. So let's bring up a picture to show an example of what we're talking about before we give some statements. So here I have the natural log function, and this is the line y equals x, and this is the function e to the x. So these two functions are inverses. So this is the two functions we're just going to consider as an example. So if this statement is true, then the following three statements are also going to be true. The first statement says if f is continuous on its domain, then the inverse function is going to be continuous on its domain. And you can see in this domain of natural log from 0 to infinity, the natural log function is continuous, and e to the x is continuous on its domain, which is negative infinity to infinity. So that first statement has to be true. Let's take a look at the second statement. The second statement says if f is increasing or decreasing on its domain, then the inverse of f is increasing or decreasing on its domain. Here we see the natural log is increasing on its domain, and so too is e to the x, increasing on its domain. And let's go ahead and take a look at a third statement. So this third statement says if f is differentiable on an interval containing c, so this function is clearly differentiable. Let's consider c be 1. If f is differentiable on an interval containing c, let's say it's 1, and the derivative of f at c, so you can see here the function is clearly differentiable at that point, and f prime of c is not equal to 0. That is, the slope of the tangent line at that point isn't 0, meaning that the slope of the tangent line isn't horizontal, because if the slope of the tangent line of the original function is horizontal, that would mean the slope of the tangent line of the inverse would be vertical. And of course we know if the tangent line is vertical, the function is non-differentiable at that point. So that's what this caveat is saying, that if the derivative here doesn't generate a horizontal tangent line, then this function f negative 1, the inverse of this, has to be differentiable at f of c. So considering x equals 1 or c equals 1, the natural log of 1 is 0. So this function should be differentiable at 0. And you can see the tangent line exists. This function is continuous, so it does have a non-vertical tangent line here, so this function is differentiable at f of c, which is 0, x being 0. Now this concept leads us to a discussion of the derivative of an inverse function. The derivative of an inverse function is given by this expression. Now before we begin with a detailed explanation here, you may be wondering, what's the big deal? Why are we considering the derivative of an inverse different than the derivative of any other function? Well, the answer is there may be times when you want to know the behavior of an inverse of a function, but you don't have the inverse function. And sometimes it may be symbolically very difficult to find the inverse of a given function. So it'd be nice to have a mechanism where we could determine the behavior of an inverse function without actually having the inverse function to work with. And that's the whole purpose behind this. So let's start by saying that f is a function that's differentiable on some interval I. If f has an inverse g, then g is differentiable at any x for which this expression, the composition of f prime at g of x doesn't equal 0. This is also true. So the derivative of the inverse, g of x being the inverse, is equal to 1 over the derivative of the function evaluated at the inverse. And this is the caveat here where this denominator can't be 0. Obviously, this inverse function, this inverse derivative wouldn't be defined at that value. So let's take a look at where this thing comes from to see if we can make some sense of this. To start with, let's consider f and g being the inverse of g. So g is the inverse of f. Then we know that this has to be true, because in order for f and g to be inverses, the composite of f at g has to be x. And the reverse is also true. G of f of x must also be x. So we start with that piece. Let's go ahead and differentiate on both sides. So the derivative of x is 1, and the derivative of f of g of x is just the chain rule. That's the derivative of the outside, which is f of x. That gives us f prime, evaluated at g of x, times the derivative of the inside piece, g of x. So that's g prime of x. So that's just the chain rule. The derivative of f of g of x is f prime g of x times g prime of x. Now that's all we're doing here is we're solving for g prime of x. So we're going to divide both sides by f prime of g of x, and that gives us 1 over f prime of g of x equals g prime of x, which is this original statement. Now, what's fascinating is I'm sure you find all this abstraction. Let's go ahead and do an example to see if we can solidify this idea. Let's start with this example. F of x equals 1/4 x cubed plus x minus 1. We're going to take this in two separate stages. The first stage is we're going to determine what f inverse of x is when x is 3. In other words, f inverse at 3. So I'm going to go ahead and work it, and then I'm going to walk you through my solution step by step. And before I do that, let me give some background and setup here for what I'm going to attempt to do. I'm not actually going to find the inverse of this function. What I'm going to do is use the reflection property of inverses. That is, we know that f of x and f negative 1 of x, f inverse of x, are reflections across the line y equals x. That means that the x's and y's swap places. In other words, the input, the domain of the inverse, is the range of the original function. And the range of the original function is the domain of the inverse. So the x's and y's swap. The domain of one is the range of the other, and the range of one is the domain of the other. So considering that I want to find out what the inverse is at a domain value of 3, then I want to consider what the original function is with a range value of 3. So I'm actually going to set this equal to the domain value here, because the domain of inverse is the range of the original. So I'm going to set this thing equal to 3 and go ahead and solve from there. So here's my start. I set the original function equal to 3, and then I'm going to pull the 3 over, and I'm going to find out where this value is 0. In other words, what x value generates a 3 as an output. So if this domain value, whatever this domain value for the original function, that's going to be the range of this. So the domain value here that generates a 3 from a range standpoint gives me the range of this guy. It'll find f inverse of 3. So that's what I'm doing here. Now what I'm going to do is I'm going to use the rational zeros test. Rational zeros test says that if this function has rational zeros, they exist at the factors of the last term, the coefficient of the last term, the constant term, divided by the coefficient of the leading term. And I'm going to use the factor theorem, which tells us that if f of c equals 0, then x minus c is a factor of that expression. And thereby, c would be a 0 of that function. So let's go ahead and pull up the calculator. And here I've entered the expression into the calculator, the original function. And what I'm going to do is I'm going to go ahead and set my table setup to ask mode for the independent variable. This is going to allow me to enter values, any value I wish, into the table. And I'm going to test function f for 1, -1, 2, -2, 4, -4, and so on until I get a value of 0. So let's try 1. That doesn't work. -1. That didn't work. 2. And 2 works. So we can see that f of 2 is 0. That means x minus 2 is a factor of this expression. Therefore, 2 must be a 0. Now to find the remaining expression, I'm going to do a synthetic division. So I'm going to divide this expression by x minus 2. And so we put in the coefficients. This is just synthetic division. And we come up with, in fact, this is a factor. And this is our remaining quadratic. And when I put the actual x values in, the remaining quadratic, after I've divided this by x minus 2, I get 1/4 x squared plus 1/2 x plus 2. And you can tell, because of all the positive coefficients, this has no real solutions. So therefore, the only solution that I get is 2. That tells us that f to the -1 of 3, the inverse of f evaluated at 3, is 2, because f of 2 equals 3. If I put a 2 in here, I would get a 3 out here. And so that answers our first question. F inverse evaluated at 3 is equal to 2. Now let's look at our second question. What we're going to do now is we're going to find the derivative of the inverse at x equals 3. We're going to utilize this value that we just got to evaluate this. Let's go ahead and pull up the work and I'll step through it. The derivative of the inverse evaluated at some x value is equal to 1 divided by the derivative of the original function evaluated at the inverse, f -1. So g of x would be f -1 of x. That's equivalent to the inverse of f evaluated at 3 is equal to 1 over f prime evaluated at f -1 of 3. G of 3 is f -1 of 3. And down here we got f -1 of 3, which is equal to 2. So we need to have the derivative of the original function. So if this is the original function here, this is its derivative. Then we take this and evaluate it at 2. So 3/4 times 2 squared plus 1. And when we evaluate this out, that clearly becomes, this 4 cancels that 4 out, and it's 1 over 3 plus 1, which is 1/4. So we've actually found the derivative of the inverse at some value without actually finding the inverse function, which is a pretty powerful tool. I have several more examples that I want to run through, but I don't want to rush through. So I'm going to end this part here, and we'll pick up the next part with some more examples of finding derivatives of inverses. So I will talk to you in the next video.